Hi class, we are on to chapter 8. We're going to start off chapter 8 with some preliminary theory. So we're going to talk about linear systems of differential equations. I highly suggest that you review the appendix for matrices. In the back of this textbook, again, we're using the ZIL if you are not in my class but just watching this anywhere. But you should have some familiarity with matrices, how to add and subtract matrices together, what the identity matrix is, finding determinants of matrices, which you should know from Calculus 3 if you have not taken a linear algebra class. I'm going to use a couple of linear algebra methods in this section because they're easier than calculus methods. However, you should know how to do a majority of these things, right? So make sure you know the identity matrix. Make sure you understand how to multiply matrices as well, okay? So that's going to help you out a lot. If you don't know how to multiply matrices, you will have some problems in this section. As long as you know what the identity matrix looks like, you should be okay as well. But the determinant is a major portion of this, as well as knowing how to solve a system of equations in augmented form, right? So basically, like the first thing you learn in linear algebra, you may have learned it in pre-calculus at some point. You don't learn it in calculus. So if you have linear algebra background, this is going to be a breeze for you. If not, I suggest that you go to my linear algebra section and review a video or two from there. You'll get used to it as we go through in these videos, the methods that I'm talking about, but you know, the more linear algebra you have for this section, the easier it's going to be. So again, if you're in my class and you're using these as a study tool, as a lecture tool for my course, then please review that section. And if there's stuff you're not familiar with, do the example problems and familiarize yourself with those things. Very important here, okay? So if we have a linear system, okay, where we have the derivative of the first function with respect to t is written as such, right? So it's written in terms of the other functions that are going to be present times some sort of functions, right? So we've seen this before where this could be, I don't know, like sine of x times whatever my function for x1 is going to be, right? Plus x squared times whatever my function is going to be here. So, you know, it's just some equations. And we're going to have this repeated for each function that I have in my system, right? So the derivative of x2 is going to be the same thing, where these are now different functions as well, right? And so forth until I run out of functions, right? So if you notice, I have n functions, and I have n functions plus a forcing function here. Okay, so f1, f2 up to fn would be my forcing function. So this portion right here, without the forcing function attached and without my derivatives here, create a matrix, which we'll get into in a second. This matrix has n elements, right? 1, 2, 3 to n, and n elements 1, 2, 3 up to n. So it's n rows and n columns. Okay, the columns go this way. So there's 1, 2, up to n of them, and there's 1, 2, up to n rows. So we call that an n by n matrix. Okay. Now, if each of these forcing functions on the end are 0, we have a homogeneous system. Okay. So again, the appendix section in this textbook, the ZIL textbook, is appendix 2, right? So go over that, review on matrices. Again, talks about how to add, subtract, how to multiply, determinants, and solving an augmented system. Okay, so we can rewrite this system now in several other forms. If you're a linear algebra student, you've seen several forms that we can rewrite a system. But for us, we're going to write it as a vector full of my derivative functions, an n by n matrix, and if this is present, if these are non-zero, if it's non-homogeneous, this would be a vector of forcing functions. So we write these as a matrix equation, right? So it's going to have vectors and matrices. So here x prime is my vector full of x1 prime, x2 prime up to xn prime. A of t only contains the coefficients here, these coefficient functions. It only has a11t, a12t, so forth and so forth. It does not contain the x1s and the x2s up to xn's. That's what this vector is, right? So again, if I'm to multiply this coefficient matrix times this vector, this is the result that it gets, right? Plus my forcing function. So without looking at it in terms of t, I can just write x prime equals ax plus f. So again, since this is not a linear algebra course, the notation I use is boldface. If there is a boldface letter symbol, that means it is a vector. If it is non-boldface, it is not a vector. In this case, it's going to be a matrix, right? Previously, this would have just been a scalar. So I'll let you know when we have a scalar value, like a real number. If not, for chapter 8, assume that it is a matrix, right? This n by n matrix that we have here, let's talk about that as well. So each of these notations here, again, from Calc 3, you should know at least this much, right? The first number tells you what row you're in, right? So 2 means I'm in the second row. This second number tells you what column. So I'm in the second row, second column. I'm in the second row, nth column. A good way to remember that is R, row first, column second. RC, RC, row, column, RC, cola, remote control, right? The R is first, the row number is first, the column number is second, okay? It's not super important here, but that is important for linear algebra stuff that you have to go over. So here again, the boldface notation indicates that we're talking about a vector. So the boldface x prime is this vector. It's the vector full of the derivatives of the x functions that we have, okay? This is going to equal, right, my a's, right? All of these coefficients, whether they're functions or constants. Most of the time what we're going to be doing for this textbook is they're going to be constant values, right? So this is only those coefficients. X is these functions being non-derivatives, right? And then f is all of those forcing functions that I have, right? And again, this should not be capital F. These should be lowercase f. So apologies for that. I think I just saw the capital F and decided to write them all in capitals, okay? But these are these forcing functions that we have here, all right? This vector x is our solution vector. This is the thing that we're after, okay? My solution vector contains all of my solutions. x1 of t is some function. x2 of t is some function. Those functions are the solutions to the system, right? We've already dealt with systems like 3 or 4 times already, but not as a system of equations. We've used differential operators to solve it algebraically, and we've used a Laplace transform, right? So here again, each of these x sub I of t functions is differentiable over our interval of existence. They have a shared interval of existence in differentiability, right, which we call I. A is called the coefficient matrix because it only has the coefficients from our differential equations. And f again is our forcing function vector, okay? So just a little bit of practice. Let's consider this system. Very, very easy system to work with. We've dealt with systems before, but we're just going to practice taking these and writing it into these forms, right? Here we go. So if I want to write in this form where it's x prime equals a times x, again, notice there's no forcing functions here, right? They're homogeneous. What we're going to do right now is we want to verify that this is a solution. Okay, so we're kind of going over this just like we started differential equations way back in chapter 1.1. I said, hey, here's differential equations, here's how they work, here's a solution, let's verify that they're a solution, right? Some of you guys are not great at that, but let's go ahead and talk about this, okay? So again, remember, you can always verify a solution in this course. So if you ever wonder if your answer is correct or not, just verify your solution. If your solution doesn't work out in your system or your equation, then you're wrong somewhere and you should figure it out and come in, fix it, okay? So In order to figure out if this is a solution or not, I need to apply it here. So the way that this works is I'm writing in vector form, but this is multiplying times each term here. So I can write this, if I wanted to, as x1 and x2 separately, where x1 would be negative 3 e to the negative 5t plus 8. And x2 would be these bottom coefficients, right? 3 e negative 5t plus 12 would be my second solution. So as a matrix, okay, for this system, I have my x prime equals my coefficients, negative 3, 2, 3, negative 2, times x, right? X prime equals ax. X prime equals ax, no forcing function. Okay. Or, more importantly, this is the way you're normally going to see it. I'm not going to typically write it this way unless we're solving something. Normally you will see it written this way. Solve this system. X prime equals your coefficient matrix times x means this. Okay. Which means this. Right? So that's 3 different ways of writing the same system. So if we want to, we can also rewrite our solution, as I said before, as their separate equations, x1 and x2. So I'm just going across the top. This is my constant. This is my constant across e negative 5t. Same thing here. Okay. x1, x2, x1, x2. So to verify them as solutions, I can just take this as it is now and plug it in as I need to. Find the derivative of x1, have this on one side, and then take this and multiply it times negative 3, multiply this and multiply it times 2, and show that when I work only one side, it equals the other side, right? And then do that again here. In order for this to work as a system, it has to work for both. It cannot work for only one. It has to work for both equations together, right? So, x prime equals the derivative of my x function. I can do this all at once if I want to. And I get 15 equals negative 15 e to the negative 5t. This is a constant vector. It goes away, right? Notice that if I did this piece by piece, this derivative is 15 e to the negative 5t. This is gone. This is negative 15 e to the negative 5t, and this is gone. But I can do it all together at once as a vector equation, right? So this turns into negative 5 in front, so this scales up by negative 5. These are both constants, they just go away. So this is my x prime vector, okay? Now the next thing I want to do is I want to take my equations and I want to apply it to this side and show that I get out 15, negative 15 times e to the negative 5t. Okay, so now I'm going to work, so that's the left side. I'm going to work the right hand side now, right? So there's no forcing function for this problem. So a times x means I have my A matrix times my solution vector x. Okay, so again, this is where it's important to know how to multiply. So I'm going to multiply this vector times this matrix, and then I will multiply this vector times this matrix. Now in order to do that, I can multiply this e to the negative 5t into both terms if I want to, or I can leave it out, it's fine. I think I actually put it in, but I'm going to distribute this. Okay, so it's important to know, for those of you who have not taken linear algebra or are not familiar with matrices, if I am multiplying a matrix times something on the left hand side, when I distribute that, this matrix needs to always be on the left hand side of my distribution. So for instance, I could not have this and then these two be swapped. So again, apologies, this should be multiply. Okay, this is going to be multiply, not a plus. I'll fix that in the write-up. But I cannot have this matrix being multiplied on the other side. It has to multiply on this side, right? So when you multiply a vector times a matrix, if you're not familiar with that, this term multiplies with this first term, gives me 9. The second term multiplies with this term, which gives me 6, and I add those together. So this row basically does a dot product with this column, okay? And that will give me the first entry. This row will multiply, will dot product with this column and will give me the bottom entry, right? So -3 times -3 is 9, plus a 6 is 15, right? Same thing here with the bottom. -3, or 3 times -3 is -9, but the -6 is -15 on the bottom. Here, remember, I'm not actually adding this. This is being multiplied. This is an error in my write-up, but I'm going to have -24 plus 24. So that's 0 on top. This row times this column gives me 3 and 8 is 24. -2 plus 12 is -24, so that adds to 0. And I got the exact same thing for when I took the derivative of my solution vector versus when I multiplied my solution vector times my coefficient matrix, right? Okay, now all of the other properties that we had from this course so far, they all apply here still, okay? Things like the superposition principle, which is how we are able to add the general solution vector to the homogeneous equation to the particular solution to the non-homogeneous equation, right? We're able to add two solutions to get a single solution. That property still applies. It's a superposition property, okay? The property of linear independence of my solutions still applies, okay? So everything that we've done so far, it doesn't change just because we're in a system now, right? We're really just adding to the complexity because we have things that are related to each other, but it is not changing the properties that are inherent, right? So again, note that this could be considered as my x1 solution and this as another solution, and both of those work as solutions to my system. So for instance, if I were to not even have this constant vector here, and I took this derivative, I would still get this solution, okay? Since when I multiply this times this, it goes to 0, this times that would still give me just that solution, right? It would be the exact same thing, right? So this by itself is a solution. x2 by itself is a solution. The derivative of this is 0. This vector times my coefficient matrix is 0. I would have gotten 0 equals 0. It would have given me out just 0, whereas this gives me equality. Okay, so both of these by themselves are a solution, and the superposition of these two solutions is also a solution, right? So in both of these solutions, x1 plus x2 creates my solution vector of x. Okay. This vector x is an x1 plus x2. They are linearly independent from each other, which is why the superposition works. Okay. Right. So x equals x1 plus x2 is a solution, and it's a solution because they are linearly independent. Right. So also note that if we had the initial conditions of x1 of 0 equals 5 and x2 of 0 equals 15, we would still have our solution, right? So x0 of 0 would be 5 and 15. So what do I mean by that? Look at my solution matrix here, okay? Okay, here. If I plug in 0, I get -3 plus 8, right? Which is going to give me 12. And then I'm going to have 3 plus 12 is 15. Sorry, -3 plus 8 is 5, right? And 3 plus 12 will give me 15. So if I plug in 0 here, I will get 5 and 15. So if this is my initial condition, my solution satisfies that. So basically what I'm trying to say is you can have initial conditions as well in a system of equations, okay? So let the entries, so existence of a unique solution. So again, we need to make sure that a solution exists and that it is unique. So if we let the entries of the matrices a of t and f of t be functions, again, this is not necessarily a matrix, it's a vector, but we can call them matrices, it's fine. So let these functions be continuous on a common interval, which we'll call I, that contains our initial point. In this case, my initial point was t equals 0, right? So if my initial point exists for my forcing function and for my coefficient matrix, then since backwards E means there exists, this exclamation mark means unique. There exists a unique X to that initial value problem. So exist, and that existence of that solution is a unique solution. Okay. So x prime equals ax plus f such that x at t naught equals some initial vector, right, on my interval. So basically, as long as it shows a common interval and that common interval houses my initial point, then there will be a unique solution to that IVP of system of equations. So again, note from our previous example that -3, 3 and 8, 12 are linearly independent of each other. I cannot add these matrices together in order to get the other one out, right? They're completely different from each other, right? They're not constant multiples of each other. If I had a third vector here that only had 2 elements, they would no longer be linearly independent. Again, if you're a linear algebra student, this should be second nature to you at this point. But for those of you who are not, basically it boils down to, can I multiply this by something and multiply this by something and add them together and get 0 out? If that's true, they are not linearly independent. If the only way for me to multiply this by something and multiply this by something and add it together to get 0 out is if the thing I multiplied by is 0, then it is linearly independent, right? So it basically means that if the only solution to this is by multiplying this by 0 and this by 0, it's linearly independent. If there's any other solution, it is not linearly independent, right? So for instance, if I can multiply this by 1 and this times -3 and add them together, I would get 0 out for both of these. They depend on each other. They're linearly dependent. Okay, so this is the a small minor definition of linear independence, right? And we call this the trivial solution, which we've talked about before, right? So we have another way of talking about linear independence, which is looking at the determinant. Okay, so let's say that we have a vector x1, x2, so forth and so forth, up to xn, all be solutions, vectors of a homogeneous system on an interval I. Then the set of solution vectors is linearly independent on I if and only if the Wronskian is non-zero for every value of an input that we have inside of our interval. Okay, you guys have seen the Wronskian before. It's the same exact thing. If these vectors happen to not be functions, but they're just values, you need to take the determinant, and as long as the determinant is not 0, you're fine, and they'll be linearly independent.